paint things, make things, change things.
The science behind aluminium anodizing. Have you ever wondered why anodized aluminium is so durable, corrosion resistant, and available in so many vibrant colors? The secret is that anodizing isn't a paint, a coating, or a plating process. Instead, it actually transforms the surface of the aluminium itself. Aluminium naturally reacts with oxygen in the air, forming a very thin oxide layer. This invisible layer protects the metal from corrosion, but it's only a few nanometers thick. Anodizing uses electricity and chemistry to grow the natural oxide layer thousands of times thicker. The new layer becomes extremely hard, transparent, and permanently bonded to the aluminium. Unlike paint, it can't peel or flake off because it actually becomes part of the metal. Even more interesting is what happens at the microscopic level. As the oxide layer grows, it develops millions of tiny pores. These pores are invisible to the naked eye, but they are the reason anodized aluminium can be colored. They act like microscopic containers, absorbing dye deep inside the oxide layer. Once those pores are sealed, the color becomes locked into the surface, creating a finish that is both attractive and durable. Today, I'm going to anodize two identical aluminium sockets and compare the results. One small change during the process makes a surprisingly big difference in the final finish. Let's get started. The first step is surface preparation. Before anodizing, the aluminium must be perfectly clean. I begin by preparing a caustic soda solution. The aluminium socket is immersed in the solution to remove the existing oxide layer, along with any grease, fingerprints, machining residue, or other contaminants. This step creates a fresh, uniform aluminium surface. Any contamination left behind could prevent the oxide layer from forming evenly and would become visible in the final finish. After the caustic soda bath, the part is thoroughly rinsed with clean water to remove every trace of the solution. Now, it's ready for anodizing. For the electrolyte, I'm using a 10% sulfuric acid solution. The aluminium socket is connected as the anode, which is where the name anodizing comes from. The counter electrode completes the electrical circuit. The power supply is set to 1.5 amps of direct current, and the process runs for 30 minutes. Now, the chemistry begins. As electrical current flows through the electrolyte, oxygen atoms combine with the aluminium surface to create aluminium oxide. Unlike rust on steel, which weakens the metal, aluminium oxide is extremely hard and actually protects the material underneath. At the same time, sulfuric acid slowly dissolves tiny portions of the newly formed oxide. These two reactions happen simultaneously. One reaction builds the oxide layer. The other creates millions of microscopic pores throughout its surface. This balance is exactly what makes anodizing possible. Without those pores, the aluminium couldn't absorb any color. While the oxide layer is forming, another reaction is taking place. Oxygen gas is continuously released from the surface of the aluminium. Those tiny bubbles may seem harmless, but they can create a problem. If a bubble stays attached to the surface, it blocks the electrolyte from touching that area of the aluminium. Where the electrolyte cannot reach, the oxide layer cannot grow properly. That means the dye won't be absorbed evenly later in the process. We'll see the effect of that in just a moment. After 30 minutes, the anodizing process is complete. The oxide layer is now fully formed, but the pores are still open. That makes this the perfect time to add color. I prepare the dye by dissolving powdered dye in warm water until the solution is completely mixed. The anodized aluminium is then immersed in the dye for approximately 3 minutes. The dye molecules travel deep into the micropores, almost like water soaking into a sponge. At this point, the color is inside the oxide layer, but it isn't permanently locked in yet. To finish the process, the pores must be sealed. The part is placed into hot water. The heat hydrates the aluminium oxide, causing it to expand slightly and close the microscopic pores. As those pores close, the dye becomes permanently trapped inside the oxide layer. This final step greatly improves both corrosion resistance and color durability. Now, let's compare the two parts. The first aluminium socket developed numerous white spots across its surface. These spots appeared because oxygen bubbles remained attached during anodizing. Each bubble blocked the electrolyte, preventing a uniform oxide layer from growing underneath. Without a proper oxide layer, those areas couldn't absorb the dye, leaving visible white defects. For the second socket, I changed only one thing. Every 5 minutes, I gently agitated the part inside the electrolyte. This simple movement released the trapped oxygen bubbles before they could remain attached for too long. Fresh electrolyte was then able to contact the entire surface continuously. The difference was immediately obvious. The second socket showed far fewer white spots, much more consistent color, and a noticeably more uniform finish. It's a great reminder that successful anodizing isn't just about using the correct chemicals or electrical settings. Small details like proper cleaning, stable current, solution temperature, timing, and even removing tiny oxygen bubbles can dramatically improve the final result. Anodizing is a perfect example of chemistry and electricity working together to transform an ordinary piece of aluminium into a stronger, more durable, and more attractive material. And sometimes the difference between an average result and an excellent one is nothing more than a gentle shake every few minutes. If you enjoyed this experiment and would like to see more projects exploring the science behind manufacturing, electronics, and engineering, don't forget to subscribe and join me for the next one.